Hello, students. We need to make some videos for second semester. Isn't this fun? I'm going to try something different and use a tablet and whiteboard to draw. So, anyway, um, these are supposed to be going over just the sort of basics. This is the minimum stuff that you need. Obviously, you're going to have to study a bit and learn a few other things. But I'm trying basically to tell you what's on the homework in a sense. So, if you're starting with chapter 19 and you're going to look at certain sections of chapter 20 as well. But the gist of it is this week we're doing temperature and heat, and then how energy is transferred. So there's essentially four sets of things here, right? And so we're going to try to go through those. There's an assumption that you've been in science classes before and you understand at least what temperature scales are, right? You understand that um, you can go from temperature in Fahrenheit to temperature in Celsius and vice versa. Right? I'm not going to write it out here. You can look that up. And you can also look up in your text others, and I'm assuming that your seniors, you've come from either biology or chemistry, and you've at least talked about chemistry. Sorry, you talked about temperature somewhere in those classes. Um, what I will say is that there's a different understand. Temperature is a thing you measure, and they may or may not go into what it actually is. And so I want to make sure that I'm covering that reasonably. When we talk about temperature, it is eventually going to be, all right, why can't I draw anything? We're eventually going to talk about temperature being an analog for energy. And so we can eventually express the energy, the the internal energy will look like some number of particles times a constant times temperature. All right. So if you've been in chemistry, this is starting to look reminiscent of the ideal gas law, which is what we're going to cover next week. All right. So the gist of this is temperature is a way of coming up with the average energy of particles in a material, in a fluid or a object or a gas. Is It's not the energy of every particle. They're not uniform, and the energy is going to look something like a plot here: frequency and speed, so energy. And the plot will look something like that, roughly. And you'll see this plot later, but it'll be, instead of energy, it'll be velocity. All right, so you'll see this plot a few different times, and that's okay. The gist of it is we can identify sort of an average energy, and this will be a function of nkt. And we'll explain what n is the number of particles in the gas, so it's some measure of the amount of stuff. K is a constant, and T is temperature. Okay. So we'll get into that in a big deal, but you've seen some of the other stuff going on. That's okay. All right. Basically, you've seen the bit about temperature. You know, make sure you understand what degrees. Right? Make sure you understand what that is and what degrees Kelvin are, which you don't actually say degrees Kelvin, you just say Kelvin. Right? And so there's some stuff going on in both of these, which we'll explain later. But the gist of it is the size of these measurements of temperature are the same. It's just where they put zero at. And for degrees Celsius, 0 degrees is where water freezes. That's how it's defined. And it's defined slightly differently, but for all practical purposes, water freezes at 0 degrees Celsius and water boils at 100. All right, we'll switch colors here. All right. So for Kelvin, 0 is defined as no energy. The particles in the material, whatever they are no longer moving at 0 degrees Kelvin or at 0 Kelvin. And then the size of the degree is the same as Celsius. So we'll have here 1 Kelvin is 1 degree Celsius. This is a delta T thing. Anytime you use delta T, the units are interchangeable. You should stick to one consistent unit and it should be Kelvin. Do not always go to Celsius unless it's completely Celsius everywhere. Now, the other side of it is you'll have things that are talking about the temperature of an object, not the change in temperature, but the actual temperature. And that's why I mean always do Kelvin. That's important. All right, so let's get into the things you actually need for this first homework. This first homework is how length changes with temperature and in heat in an object. You've seen this if you took chemistry. If you took biology, I'm going to try to cover it for you guys, but understand that, you know, this is the thing is I teach to a wide audience. And so some people will get this because they saw it last year, and some people may get it and they may not, but they didn't see it last year. So we have length. And let's take a object here. I'm going to draw it out so it looks like this. And then we're going to take and identify particularly the amount at which it changes. Right. So this part is the original length. This is what we're going to call L0. If we define this L0 at some temperature, it's at a known temperature, then this little extra bit is what happens if there's a change in temperature. What is the change in length? Well, that's solvable. What you do, and this is an empirical method. You just find a thing and you heat it up to different temperatures and you measure its length over and over. And what we find is that there's an empirical formula. The change in length is a constant times the original length of the object times the change in temperature. Or to write it in derivative terms, dl dt is alpha L initial, which is a constant. It's a linear function. If you heat an object by 10 degrees and it grows by 1 centimeter, then when you heat it by 20 degrees, it grows by 2 centimeters. All right, it's a linear function. So the trick here is going to be where do we get our alphas here? Right, is we have this thing, and we need to define that somewhere. And the way we do that is by looking it up. We've done this measurement a bunch. So in your textbook, page 539 at the top has a bunch of materials, which are generally going to be the materials that you use in homework problems and exam problems, that sort of stuff. And if you need this number, and we're not asking you to derive it, you'll always be given it. You don't have to derive it yourself. So we're always going to do some sort of thing where we want to talk about length changes, and we're going to use temperature changes to inform how much the length changes. And let's do an example. So let's add a page here to this. So let's say you have a slab of concrete. There's your slab of concrete. And we're going to measure this distance to be 1 meter. And that's not unreasonable. If you've seen concrete laid out on streets, it's between 3 and 4 feet. A meter makes some sense. Now, you've also seen cracks in the sidewalk. And you've seen two different types. You've seen the purpose left cracks, which means that if we have another slab of sidewalk right beside it, there is an on purpose left little area in here. Right. Well, that's what we're want to talk about, is essentially why those are left there. Now, you've also seen other cracks, and they might run through something like in the middle of the slab. And that's because maybe not enough room was left. Right. So we're going to erase some of this. Ooh, I erased too much. All right. We'll put that back. It's okay. So here's our slab of concrete. We want to know how much it grows when you lay this slab. It's 1 meter long when the temperature is 10 degrees Celsius. But what we're going to do is say, well, it's a hot day today. So we'll say it's 35 degrees Celsius, and we want to know the change in length. And that's not too terrible. The idea is we have this one formula and it's plug and chug. The change in length looks like this constant times the original length times delta t. That should be capital T. So you'll have to also bear with me. I am not used to tablet use. This is a new thing. I like it. I want to use it for the college, but I'm more used to pen and paper. So what we would do is figure out the stuff on the right side of this equation. Alpha here is a constant. We go look it up for concrete. It is 12 times 10 to the minus 6 per degree Celsius. What that means is it changes length. The fractional change in length is 12 parts in a million per degree Celsius. Right. So we have that constant. And then we'll have our original length is 1 meter. And then our change in temperature is 25 degrees Celsius. And I kind of want to be careful here, so I'm going to write down here as an aside. When we do delta T, there's two forms of it. It is almost always T final minus T initial. But sometimes it is T hot minus T cold. Sometimes you just want to know the difference. Other times you actually want to know the direction of the change. Sometimes you want to treat delta t like a vector, at least in a sense of you have a number line and you want it to go up or down. Other times you just want an absolute value. Sorry, so you might have something like that. Anyway, that's an aside that's not necessary. The point is we need to calculate this out. And when we do it, we will get that a sidewalk will change 3 times 10 to the minus 4. And in our units here, we have Celsius canceling, and we'll have meters. And this is 0.3 millimeters. That's our delta L. Right. So these sidewalks, and they're laid, and they've got a significant crack, like half a centimeter, 5 millimeters. And that's because you'll have multiple slabs expanding and contracting. And, we give you a number for this, but it's not perfect. The gist of it is these slabs expand and contract, and you leave space between them. So this sort of problem is exactly what you're doing in number 1. It's what you're doing in number 2. It's useful. Now, we mostly focus on the length change, but there is also a volume change. Let's get a thing going here. All right, say delta V. That's going to look the same way. You're going to have some constant times the original volume, which is measured at some initial temperature, times the change in that temperature. And if you go through your text, there's a justification for what's going on is if you have an object, so let me try to draw a big box. There we go. So there's a cube. This thing is going to length expand in 3 directions. It's going to expand upwards and downwards. It's going to expand across the board, left and right. And it's going to expand outwards. And so